starting the actual proof, let me make one remark, remark about the formula. So, compare it with the following. So, it's from probably real analysis. Imagine that you have some function g depending on your variable you integrate, and also on some parameter lambda. Right? And then you introduce a bigger function f of lambda, which is integral, doesn't matter which integral, so maybe from a to b, g of t lambda dt. Then sometimes, and there's a study in real analysis when this works, sometimes if you take this f and differentiate, it's just integral of derivative in lambda of this thing. So have you seen such formulas before? It's called parameter differentiation. So now compare. So let's take a look at this formula. This expression. So this will be our g of z, but also z norm, right? So it's a function which depends on z, our parameter of integration, and also the point where right? Good. Now, so as a function in z node, so this the numerator is just constant, so we can ignore it. But denominator is So let's take the function 1 over say a minus z, or maybe not to mix with z, a minus x, and differentiate it once. We'll get 1 over a minus x squared. If we differentiate it twice, we'll get 1 times 2, and then here cube. Okay? If we do it 3 times, then we'll get 1 times 2 times 3 to the 4, and so on. So 1 over a minus x nth derivative is n factorial 1 over a minus x to n plus 1. Okay. Now, I'll write something strange. I'll write d over dz node applied n times to the function f of z, z minus z node, like this. So then, just by what I wrote above, this thing will be equal to n factorial f of z So z is not our parameter of differentiation. Z minus z naught to n plus 1. So, so if we already know, so it's not a proof of the theorem, it's just something assuming this kind of rule works, and there are conditions for this rule to work in real analysis. So it's better the way to remember the formula than a proof. So if we know the Cauchy integral formula, which is f of z naught is integral dk blah 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 f of z minus z naught dz. Then, so this is a function on z naught. If we believe so it's a quasi-proof. If we believe in this kind of thing, so let me put here star. In our situation, then we should expect nth derivative of f at z naught to be equal to 1 over 2 pi I integral over the same thing of d over dz naught applied n times to f of z minus z naught dz. So again, I'm not producing a proof. A proof will be different. But at least it's an easy non-proof, which in a way illustrates why this formula is natural. So let's now substitute our calculation. So nth derivative of this will be exactly n factorial over 2 pi I integral over the same thing of f of z minus z naught to the power n plus 1 dz. N of no proof. Okay. So what stands? Let me repeat the idea. What stands here with this factor is indeed nth derivative of this expression when you differentiate by the point where you center all this. Okay. And now forget all this, or remember this as a way not to make a mistake in the formula. But let's prove the theorem. So step 1 is expand 1 over z minus z naught at a different point. So we could, of course, express this as the known geometric series at z naught, but we want to expand it at A. So let's talk about sum of geometric series. So first of all, there's algebraic formula. So the formula is that 1 minus any, so let me t to the n is 1 minus t times 1 plus t plus so on plus t to n minus 1. So this is true always. This is just equality of polynomials. Then 1 minus t to the n over 1 minus t is a partial sum. So sum m of k equals 0 to n t to the k. Yeah, so I claim so if absolute value of z is less than 1, then the limit and the sum k equals 0 to infinity z to the k converges absolutely to 1 over 1 minus z. And of course the so you define it as limit I mean at any point as limit n going to infinity 1 minus z to the n over 1 minus z. And certainly for absolute value of z is less than 0, this limit equals to 1 minus. Okay, so this is the proof, and now about the expansion. So let's do a re-expansion. So let's write one over z minus z naught as this minus plus a minus z naught. So this is 1 over z minus a times 1 minus z minus a so let's draw the picture of our integration. So we have our domain G, and then we have our disk K, A, R, and then, so this is A, and then we have Z node somewhere here inside. So in particular, since Z node is in K, A, R, absolute value of z node minus a z minus a is, well, and our z is, so runs on this, so when we integrate, z goes around this circle, so then this distance is r, and this is, so it's less than 1. So we can expand this series. So let's do it. So 1 over z minus z naught is, so first factor stays, and second factor becomes sum n equals 0 to infinity, z naught minus a, z minus a to the n. So this is sum n equals 0 to infinity, z naught minus a to the n, z minus a to n plus 1. Very good. So then this expression f of z, z minus z naught, becomes the sum n greater equal to 0, f of z, z naught minus a to the n, z minus a to n plus 1. Very good. So let's take a look at this series. So this is considered as, so we'll integrate, so as a function of z. So let's see convergence. So study convergence. So let's take f of z minus a to the n, z minus a plus 1, and estimate the absolute value. Yeah. So let's say that so f restricted. So it's a continuous function on a compact set. So then the absolute value of f of z can be estimated from above by some constant m. Yeah. So notice that from our point of view, z is a variable, so this is a constant. So it's just a number for us. So then we see that this is less or equal than m over r. To the n. So now we can apply the criterion uniform convergence criterion. So this sum converges. Thus, sum of f of z minus converges absolutely, converges uniformly. To f of z minus z. Very good. Then we can start applying Cauchy integral formula and then change the order of integration. Apply Cauchy integral formula, and then let's see. So f of z naught is 1 over 2 pi I integral over z k a r f of z minus z naught dz. And now we substitute the expansion. So what we had over there, f of z minus z naught minus a to the n over z minus a to n plus 1 dz. So change the order of integration of summation. Change the order of summation and integration. Notice that from the point of view of this integration I'm writing, this factor is a constant, so I can take it outside of integration. So this is 1 over 2 pi I sum and greater than 0 z minus z naught minus a to the n integral dk r f of z minus a dz. So and this sum still converges absolutely.
Still n plus 1, right?
N plus 1. Yes, thank you. Yes, yes, yes. So, and now take a look at the final expression. So we obtain for any z naught in KAR, f of z naught is sum n greater than or equal to 0 equals node minus a to the n. So now this is the variable, and this is just a coefficient. So as serious as expansion around A, this converges absolutely. Now let's recall, so this was one of my announcements, that in the end will be expressing holomorphic function via analytic. So right hand side is sum of power series, so it's analytic function. Right? So we get that. So by chapter 1. F of z naught being a sum of power series which converge absolutely in K A R is differentiable and its nth differential its nth derivative at this point is expressed is exactly the left hand side. I mean this coefficient. Times n factorial. Where did I get 2 pi I? I lost it somewhere on the way. So, I mean, by uniqueness of sum of power series, so we know that for sums of power series, coefficients are exactly derivatives at the center where we expand. So, yeah, it's just now just call the variable a z naught and get the formula, the generalization of Cauchy formula. Just renotate. Okay, so we obtained the proof of Cauchy integral formula for derivatives. and proved the, so this is end of the proof of the theorem. So we saw that f is infinitely differentiable given by power series. Where its coefficients. Basically like this. Great. We finished the proof, and as I mentioned, the main tools, apart from Cauchy integral formula, is this change of order of integration. So we'll see later that later we will see that under the condition of uniform convergence, we can exchange not only integration and summation, and also, so this we know already, and also differentiation and summation. So if we have sum n equals 0 to infinity fn, and series converge uniformly or locally uniformly, and each of these are holomorphic, then the sum is holomorphic, and if you want to differentiate, we can do it under the symbol of summation. Okay, so maybe I'll stop here. I don't want to start the next section.